In this video, we're briefly discussing point estimators. So what is a point estimator? Well, basically it's a single number that's used to estimate an unknown parameter that you are interested in. So for example, if I wanted to know the population mean for male heights, right? Then the unknown parameter I'm interested in is the true average male height, right? So what would I use as a point estimator in that case? Maybe the sample mean, right? So I'd go out and maybe survey 50 guys, get a sample mean height for that group of 50, and I would say perhaps this number is a good estimate of what the population mean height is for all of male humanity, right? Okay, so that's the idea. Sample mean would be a point estimator for the population mean. The sample proportion would be the point estimator for the population proportion, and then sample variance is a point estimator for the population variance. Three main ideas you want to consider when talking about the concept of a sampling distribution for a point estimator is this. Imagine a sample mean, instead of being the average for a set of measurements, it itself was a measurement, right? So what I mean by that is imagine if you had billions and billions of samples that each consisted of 50 men, and you took the average height from each of those samples, right? So for every sample of 50 men, all the different conglomerations of 50 men you could select in the world, right? So you have literally billions of samples. You calculated a sample mean for each of those. You'd now have billions of sample means, right? And if you kind of plotted them on a number line, you could kind of see what shape they form, right? If you constructed a histogram, you'd see what shape they form. So that's the first thing we're talking about when we talk about a sampling distribution for an estimator. We might ask, what shape would result if you plotted them all on a number line, right? Would it be bell-shaped, for example? Or would it be some other shape? The next thing you want to know is where is it located on the number line? That refers to its center, or in other words, its mean typically, right? So we'll talk about the mean of the sampling distribution. That's kind of the center of the distribution, where it's centered on the number line. And then finally, the spread in the distribution. How spread out is it? Is it highly clustered, right? Or is it very spread out across the number line? And that can be measured by something like the standard deviation or the variance, right? So when you think of a sampling distribution, think of three questions. What's the shape of the distribution? If you plotted all the measurements on a number line, what would the shape look like? Where is that located on the number line? In other words, what's its mean? And then how spread out is it? Or in other words, how clustered is it around that mean? So I think most of you understand where the mean is or what the mean is, right? So if I say the mean of an estimator, it means, going back to the example, if I had billions and billions of sample means, what would happen if I added all those sample means up and divided by the number of sample means? I'd get a mean for the sample means. And it turns out that mean should be very close to the population mean, and it would be the population mean if I could collect every conceivable sample, right, of 50 men. But of course, I can't collect every single sample. So the general idea is that in the theoretical sense, the average of the sample means is the population mean, which is the thing we're trying to estimate. So that's very good. So when we refer to a standard error of an estimator, we're saying, hey, look, imagine X bar, for example, the sample mean. If its job is to tell you what the population mean is, then when it deviates from its mean, which is the population mean, it's committed an error, right? So when it's not equal, when a measurement from a sample, so if I go out and collect 50 guys and I take the average height, let's say the true average height is actually 5'9", but my sample shows it's 5'8", then my sample mean is different from the population mean. And if it's designed to be an estimator of that population mean, it's just committed an error, right? It's not equal to the thing it's supposed to be estimating. So that's why we'll call it a standard error for the sample mean, or the standard error for the estimator, instead of saying the standard deviation for the estimator. But that's all it is, right? We're talking about deviations and we're calculating the standard deviation. So the standard error of an estimator is just the standard deviation for that estimator. And the way it works is pretty simple. If you have a large standard error, it means that your estimator bounces around more. It varies more from sample to sample. And since it varies more from sample to sample, it's sort of less reliable, right? Whereas opposed to if it's on the other extreme end of things, if it's very small, the standard error, it means it doesn't vary very much from sample to sample. And it's also, therefore, all the measurements or all the estimations are going to be very close to the target mean value that you're interested in. So we're going to learn this concept of unbiased estimators later, but the general idea is if this line in the center of each of these curves represents the location of the parameter that you care about, that you're interested in, then when you have very little variation like this, it means that any particular estimator you calculate from a sample is probably pretty close to the target value that you're interested in, right? So any sample mean then would be very close to the true population mean. So you could then say, hey, this is pretty close to the population mean, and that's great, right? If you want to know what the population mean is, well, I can just get a sample, calculate the sample mean from it, and then that sample mean should be very close to the population mean. And that would be true as long as this standard error is small, right? If it's larger, then of course you don't know if the estimator you have is particularly good. It could be fairly far from the target parameter that you're interested in. So that's kind of the idea. You want a small standard error, ideally, because then it means that when you calculate your estimator from a sample, it's probably pretty close to the population parameter that you're interested in. Okay, so what are the desirable traits of a point estimator? Obviously, we just talked about the idea that we probably want them to have a very small standard error. So standard error, of course, is related to the variance, right? Because standard deviation and variance are just related to each other by the square and the square root, right? So if you square the standard error, you will get the variance. So what we're going to say is the best point estimators are minimum variance unbiased estimators. What that means is that they have the smallest standard error or variance possible among all estimators that are unbiased. So the first thing we're going to look at is the estimator unbiased? There are times when you can't get an unbiased estimator, but ideally, if you have one, that's the one you want to use. An unbiased estimator is an estimator that clusters around the target parameter, meaning that its mean is equal to the thing you're trying to estimate. So, for example, if this red line indicates what we want to estimate, there are three different estimators distributions illustrated here. There's the yellow estimator here, the blue one, and the green one. So let's just use our intuition to evaluate this. You can see that the yellow values are all clustered around the target parameter in red here. So that when you calculate, say, one of these values, right? Say you have a sample and you calculate the sample mean, for example. If it lands here on the curve, it's pretty close to the population mean value that you're trying to determine. So it's really nice if your estimator looks like the yellow curve. Now the blue curve also has sort of the center, it looks like, right? So it looks like it's balanced equally on each side of this red line, but it's very spread out, right? So sometimes when I calculate a value from, this estimator, it might be way over here, right? Way far away from the real target parameter. And that isn't so great, right? That's not so great. So in other words, it's not as consistently close to the target parameter like I'd like it to be. I mean, sometimes it might be here, right? But then other times it might be wildly far away, right? And in which case, you don't know if your estimate is a good one in that case or, a bad one. Whereas even in the most extreme scenario, the yellow one is generally much closer to the target parameter in red than the blue curve. But both the yellow and the blue curve, since they're centered around that target parameter, they're said to be unbiased. That means that their balancing point or their mean is the target parameter you're interested in. Now, compared to the green curve seems to appear to have basically the same variation that the yellow curve has, but the major difference is it's not balanced or centered around the red target, right? So if you get an estimator from the green curve, it's not equal to or nearby particularly to the one you want to know, right? You want to know where this red line is located on the number line. And the green curve doesn't really help you determine that, right? It's clearly biased, which means that essentially its mean is not the same as the target parameter you're trying to estimate. So biased estimators, try to remember B for biased, B for bad. Now, it's not that you can't work sometimes with biased estimators. There are ways to adjust a biased estimator into an unbiased estimator at times. If you certainly can determine what the bias is, then you can kind of just subtract or add that corresponding amount to your estimates to make them, therefore, unbiased estimates. But don't worry about that part. What we really want to know is just the idea that what we want from an estimator is that it's got two traits. It's unbiased, first and foremost, and then it has the smallest variance possible. So between these three, we're going to discard or throw away the green estimator because it's biased, right? We want unbiased estimators. We want estimators that surround the target parameter. So we got the yellow one and the blue one that do that. But of course, the yellow one has a much smaller variance or standard deviation or standard error, right? So it's more clustered around the target, and that means that's the one we want most. Okay. So to test these ideas, let's see if we can answer this question. Which estimator would you choose to estimate the mean? Estimator A has a variance of 2.3, and the expected value, or the mean for A, is mu plus 2. So we're trying to estimate the mean, so we want the expected value of A to be equal to the mean, not the mean plus 2, right? That means that estimator A is biased. So we're going to toss that one out. We can also therefore toss out estimator C, right? Estimator C is also biased. it has a mean minus 1 as its expected value. So it's not equal to the mean. Its expected value is equal to the mean minus 1, right? So it consistently sort of underestimates, right? So that means that we want to toss this guy out as well. However, look at the variance for C. It has a very good variance, right? 1.3 is small. Now, estimator B is unbiased, right? In other words, its expected value is equal to the mean, which is what you want it to be. So that's good. That's the trait we're looking for, right? We want that to be the case. However, its variance is 4.8. We can do better because estimator D is also unbiased, right? The expected value of D is equal to the mean as well, and that's what we want. But then the variance is much smaller. So among this list of options, I'm going to go with estimator D because it has the smallest variance among the estimators available, and it's unbiased. So unbiased estimators are the things we consider. We'll toss out the biased ones. If we can get an unbiased one, we'll take the unbiased one, and then we'll go for the unbiased one that has the smallest variance.